We'll talk about some control activities. And this is a term, the term control activities comes right out of ISO 55000, the asset management standard. So we'll talk a little bit about that. And then I want to end that conversation with the value audit. Again, this is an asset management term. And so I'll show you sort of how that applies and what we need to do there. And then get in a little discussion on strategic planning for the life of the asset, spare parts. I'm not sure where all the participants in this webinar are at geographically right now in the world, but I'm calling you from Tulsa, Oklahoma in the United States. And I can tell you to me, and just my consulting around the world, and certainly in the United States, I believe that the access to spare parts, or the continuous logistical line to get the spare parts that we need to maintain our assets, I can tell you this has become the Achilles heel in the United States, certainly with this COVID-19 situation we're all dealing with and lockdown of borders and things. Access to spare parts is troubling for any maintenance and reliability organization because it's just so hard to do. It costs a lot of money and it's difficult to get spare parts because our manufacturers don't source them anymore. Nobody's making them. We got to take parts off another machine, sort of cannibalize. Access to spare parts is becoming the Achilles heel. I also want to talk about strategically skilled operators and maintenance technicians. Before this COVID-19 pandemic hit the United States, we had very low unemployment in the US. Our economy was booming. You couldn't find maintenance technicians. In fact, none of the companies that I consult with could actually find a maintenance. But even our operators have to have some skill and some talent. So we'll talk about that, and then capital and general modifications, just kind of touch on that. And then I want to finish up the day with some scenarios. And I will include the scenario with Terry that I was just talking about. So that's pretty much what we're going to talk about today. And the way I'd like to run this class is, let's go till about, I see that it's 1/4 the hour now, and wherever you are, I'm going to talk until about on the hour, and then let's take a short 5-minute break, and then we'll come back and we'll finish up whatever's left of the discussion. But again, I meant for this to be a very thought-provoking. I wanted to share some anecdotal stories, things that I've experienced. I'm sure many of you have had the same experience, and so I want you to think about that. And some of the case studies I have, I want you guys to consider what your response would be, and then I'll interject what my thoughts are. So just a real quick introduction of me. I think there's some people actually on the line that I know personally or professionally. So I just want you to see how handsome I am. That's actually a picture of me. Of course, you guys can see me right now. I'm sitting in my home office. But Chris was generous, as they have been always at LEORON. I've actually been in the business for 35 years, so you can tell I've got the hairline to prove that I've been around for a while. I mentioned before that I'm quite the student, and I hope that everyone listening continues to be a student in our profession of reliability and maintenance and engineering. And in that effort, I've authored 2 books, and you can see a little picture of them down there to the right, the Reliability Excellence Workbook from Idea to Action. I'm happy to say that spent 8 weeks as Amazon's #1 new release 2 years ago. And last year, my book on asset management came out. It was Cover Your Assets, Asset Management at Your Place and at Your Pace. And that spent 5 weeks as Amazon's #1 new release. So I was very fortunate to have a great reception for those books. I'm going to use those as sources for this presentation. I've also, again, trying to stay in the professional setting, and you get around people who are movers and shakers and innovators in your industry, and it rubs off on you. So I've also authored 15 periodicals, as well as being honored to speak 3 times at the annual SMRP conference on various subjects, and I've been the keynote speaker in many engineering and maintenance type conferences before, so I've been honored to do that. I'm also the principal instructor for North Carolina State University's Maintenance and Reliability Management Diploma Series. North Carolina State University in Raleigh, North Carolina has an exceptionally well laid out, I didn't write the course by any means, but they have an exceptionally well laid out program that's 3 modules long, and the successful graduates actually receive a diploma from North Carolina State University for MRM, which is the name of their program. So in addition to being a college professor, I'm a certified maintenance and reliability professional. I think I'm on my 7th or 8th year with that certification. I hold a U.S. patent. That's probably my biggest bragging point, is I have a U.S. patent. So I'm kind of proud of that. And then, of course, I've got a couple initials after my name too. So I like to think that I'm not so sure I'd qualify as an expert, but I like to think that I at least pay attention, and I know a thing or two about what's going on, and I'm looking very forward to sharing that with you guys. And again, I hope that we all remain students and strive to learn as we go along. I want to point out the source documents. I source down at the bottom when I'm talking about something, but I want to point these out specifically. I mentioned Ramesh Gulati and his seminal work, Maintenance and Reliability Best Practices. I'd like to say, again, I'm not sure who exactly is on the call, but if you're a maintenance and reliability professional, or if you're an engineering professional, if you're in procurement, or if you have some role in asset management or the decisions around capital assets and spending and things like this, I would strongly suggest, if you don't already, I would strongly suggest that you start a professional library. I mean, readers are leaders, and so you should have some book on your desk, things that you're currently reading. And I highly recommend Mr. Gulati's work. In fact, I'm holding up my copy. I haven't gotten him to sign this yet because I've met him several times, but I never seem to have the book in my hand when I'm talking to him. The other 2 books I'm going to reference, are books that I wrote, and you saw those just a minute ago. But some of the things I'm going to share with you are, again, this is exactly how I do it. I'm not showing you guys something I wouldn't recommend you do. If I was consulting in your business, I'd come in and I'd probably take out my book or Mr. Gulati's book, and I'd say, okay, let's go turn to this page, and here's how you do it. So I'm going to share with you some of my personal practices, and I hope if you guys find these useful, I hope that you give them a try, or at least advance your discussion and knowledge on it. So just I want to expose you guys to what sources I'm drawing from. It's my 2 books and Mr. Gulati's work as well. Again, I strongly recommend, if you don't own Ramesh Gulati's book, that you buy that. It's an exceptionally well-written book. It's very, very good, and it's very informative. Okay, so that's kind of the layout of the land, how I intend to run this webinar. And again, I appreciate you guys' attention. We'll take a break here right on the stroke of the hour. I'm going to start by talking about this concept of design, build, and install, and specifically inherent reliability. And I think I'm probably going to mention some things that maybe you guys hadn't thought about, or if you had thought about it, maybe you haven't convinced anybody else that it's worth knowing. One of the things is with inherent reliability is, what we need to understand is, when a brand new asset, when I say asset, I mean a piece of equipment. When a brand new piece of equipment arrives at our facility, it arrives with what is called with inherent reliability. The inherent reliability is really a factor of its design, how it was designed, how it was built, and in many cases, how it was installed. It could be designed really, really well, built in the best way possible, and then we kind of mess up the reliability by installing it wrong or not correctly, or we didn't install it the best way possible. So that affects the inherent reliability. So here's a concept I want you to think about. If you design a machine, a piece of equipment, poorly, and you build it cheaply, and you install it hastily, you won't have a world-class asset on your hands. You're more likely to have a nightmare for the next 25 years. Very often, it's very common. In fact, I can't give you any examples to the counter, that we expect when our machines to arrive and we get them put into production, that machine's going to be around for a while. It's going to be producing our product or providing our service. It's going to be around for 10, 15, 20, maybe even 25 years. If we do everything in front wrong or poorly, we're going to be fighting those poor decisions for the next 25 years. And I can imagine with the as I'm seeing the number of participants on this call, I got to believe that more than half of you can give anecdotal examples of how you had a machine that was just really not built right, or you're running it outside of its design parameters or something, and it's just a real nightmare to maintain. Here's a very important point, and it took me, to be honest, it took me a lot of conversations for me to even understand this myself. You can't maintain more reliability into an asset than it has inherently. So the way that it was designed, built, and installed, that's the inherent reliability. That honestly is the best that it's ever going to be. I can't maintain it more and increase the inherent reliability. The only way that I can increase the inherent reliability of an asset is to do a modification that purposely targets an increase in reliability. I'll give you an example. Most of the modifications that we do to our equipment in our plant now is not to make it more reliable, it's to make it last longer. We'll put some gussets in there, we'll put a different kind of motor because the old one's not supported anymore. We'll put a bigger sheave and a bigger belt on it to make it run faster. We're not doing modifications, not typically, to increase the reliability. We're usually modifying equipment just to make it last a little longer. So we can't maintain, you can't do more PMs, you can't do more predictive maintenance, you can't do more parts replacements, emergency, you can't do that kind of stuff to make it more reliable. It's going to be as reliable as it is when it got here. So the mission of the engineering department is to deliver an asset that has the highest level of inherent reliability. We're counting on the engineers or the project engineer, whoever it's being built, obviously by a, if it's not being built by our own company, it's often being built by an original equipment manufacturer. I'm counting on the project engineer to deliver to us and install the best machine possible. And then the mission of the maintenance department becomes to maintain the inherent reliability. And I want to just give some thought to this just for a second. The way that we fail to maintain the inherent reliability, the things that we do, not with intent of bringing down the reliability, but the things that we do that affect the inherent reliability, that is to say, make the reliability go down, is when we don't do the PMs, the preventive maintenance, at the right time, at the right frequency, when we don't look for signs of wear or degradation, we don't take action to correct it. It's when we don't lubricate it properly. That could mean don't lubricate it at all, could mean over lubricate it. It could also mean we're using the wrong lubricant, or we're mixing non-compatible greases or oils. It's when we don't tighten and torque properly. It's when we don't align things properly. It's when we just do poor maintenance that chips away at the inherent reliability. And then pretty soon, 3 years later, we find ourselves looking at a piece of equipment that was brand new 3 years ago, and we almost don't even recognize it because it is such a horrible machine. It runs poorly, it breaks down, operators hate it, maintenance people hate it. We don't have spare parts to support it. And we wonder, how did we get like this? Well, we got like that over time. We just slowly chipped away at the inherent reliability. So engineers, you got to deliver an asset that has the highest level of inherent reliability. And maintenance people, we've got to do the best maintenance possible, because what we're trying to do, quite honestly, is guard and protect that inherent reliability. So that's just a point I want to make just kind of at the beginning. Now, some of you guys might be, involved in a methodology. It's the #1 methodology in the world. It's called total productive maintenance, and it's the #1 methodology in the world for asset reliability. And it's generally thought of in 5 different categories. This one down to the bottom right would be considered maintenance excellence. And this is where maintenance typically resides. This is where we do preventive maintenance, predictive, corrective maintenance. We have a storeroom, a planning and scheduling function. We've got a CMMS, we've got a work order system. Hold on, guys, I'm just trying to navigate this. I see 5 people have raised their hand, but I'm not really quite sure how to respond to that. Let me see what we got. So I've got a note here that says maybe your mic has on your headphone has been disconnected. So I'm not sure if anybody can hear me now, but
I can
is
hear
my microphone still working?
Yeah, it's all good from my side, I believe. Guys, can you confirm, please? in the question and answer box. Just confirm that you can hear us.
I can hear you.
Yeah, we can hear you as well. I guess it's all good. Just checking. Maybe it's some, yeah.
Okay.
So we're good. Yeah, good.
Thank you for that. I hate to think I was talking to myself. Someone asked for my LinkedIn. You would find me under John Ross. Last name is ROSS, and I appreciate that. Thanks for letting me know if there's a mic problem. I'll pay more attention to that. So I was talking about total productive maintenance, and I'm drawn to this point of equipment design excellence. Another aspect of another aspect of total productive maintenance is this operations excellence. And this is where in total productive maintenance, this is the category or the area that we would identify what the operator's role is. This is where you would have autonomous maintenance, for example. That's where this would reside over here. The upper left is a category called equipment improvement. And this is where we do root cause analysis to solve chronic problems. We form small teams, and I'm sure everyone on this phone call is familiar with the concept of Kaizen. So this is where we would do our Kaizen type events. Here in the middle is knowledge. I'm sorry, every time I touch the screen with my stylus, it changes screens on me. Right here in the middle is where we have knowledge and skills. This is where we enhance the theory of operation and skills of our maintenance people and our operators. So that's in the middle. And what I'm driving down to is this last segment, and probably one of the least understood segments of total. In fact, all the, not all, but the majority of the organizations that I go to help them build a total productive maintenance approach and methodology to asset reliability, this is where they're usually lacking. This is equipment design excellence. They have interest and knowledge about all the other things, but this little area down here to the bottom, they don't have much knowledge. And matter of fact, this is probably the area they're performing the least of and doing the worst at it, if you will. Often it's referred to as design for excellence. There's other synonyms that are around this category. One of the things it takes into account is standardization of parts, and this is a very important term. If I'm going to maintain the inherent reliability of my asset, one of the things that chips away at that reliability is if I put a different part on the machine than the machine came with. Anytime I can't get the original part and I have to substitute some other part, could be almost just exactly like it. But anytime I change the machine in any way, I'm slowly reducing the inherent reliability because I'm introducing a new variable. So what I want my engineering department to do is have a standardize on the name brand, the size, the make, model of parts we're going to use. And what I'll find when I get into a standardization process is that whatever my crazy production operation is, whatever environment I'm in, hot and dusty, cold and wet, whatever the environment my equipment's running in, there are some components that seem to be robust enough to just last for a long time. I want to standardize around those parts. And the next time I design a machine or I modify a machine, I'm going to ask that those parts be used on the new machine. Why? Because they're robust. They just seem to work. They're robust. Also, my people are very familiar with them, and my maintenance guys know how to troubleshoot them. My operators know what they look like. So I've got this standardization. And if I can impart any one piece of information to anybody, I would encourage all that are listening to adopt some sort of standardization of parts. This early design excellence or design for excellence also requires shop floor involvement. It was my experience as a plant engineer, and I was guilty of this myself, of bringing in new equipment without sort of consulting with the mechanic on the floor or the operator on the floor. And I learned this lesson real early to bring those people on my project team because I need their approval, I need their engagement if I want my project to be successful. Early design excellence requires, it sort of demands that we bring shop floor involved, that is the maintenance, the average technician, the average operator, bring the people who are going to be essentially the victim of our design, bring them into the project team early on. Early design excellence also requires, and again, this is all in an effort to have the highest level of inherent reliability. I'm going to demand from, if I've got an original equipment manufacturer making the machine for me, I'm going to demand as-built drawings. Now, this is important because if you don't demand as-built drawings, they're going to give you design drawings. And the difference between a design drawing and an as-built drawing, a design drawing is what they intended to build. The as-built drawing is what they actually delivered to you. So I want to have as close to as-built drawings as possible. I want to have a complete bill of material. I tell my clients I want a bill of material in English, in writing, and electronically. The engineer is responsible to bring in the drawings and bring in the complete bill of materials. Now, again, most of you on this call you've probably had experience with OEMs. They're not likely to give you as-built drawings, and they're not likely to give you a complete bill of materials. And the primary reason is because now that you have the drawings and you have the bill of materials, you don't need them to build the next machine for you. You can hire anybody to build this machine. So these aren't things that OEMs typically give to you, and if they do give them to you, they're not complete. They're giving you essentially what they can get away with giving you. I want the OEM to also recommend suggested spare parts and a preventive maintenance, predictive maintenance strategy. I want them to suggest that. I'm not going to take their word for it because I'm going to build my own PM strategy. I'm going to take their suggestions for sure, but I'm also going to build my own spare parts listing. The reason I don't take an OEM's suggested PM strategy as the final word is because original equipment manufacturers, if you really think about it, they don't actually make anything. They built the frame, they built the cowling or the shrouding around a machine, the panels. They may have built the electrical panel, they may have bought the panel and built the backplate on it. But they didn't make the motor, they didn't make the bearing, they didn't make the cylinder, they don't make the gearbox or the coupling or the chain or the sprocket or the sheave or the belt. They don't make any of that stuff. They buy it just like we buy the spare parts. So the person who made that 25 horsepower Baldor motor, the Baldor Motor Company, they didn't know that that motor was going to be run in a wet and cold environment. They don't know what the environment or the context of operation that the parts they're making are going to be run in. And so we've taken apart, the OEM recommends that we check it periodically and grease it occasionally. That's not a real strategy. That's basically just a real quick reference to some things you need to do. So for early equipment or equipment design excellence, I need to take the OEM's recommendations and I need to build a real PM strategy and a real spare parts requirement. And then I need to also make sure I have a strategy to train my operations and maintenance people beyond whatever I've contracted the OEM to deliver. Obviously they'll bring a team in, to set it up and probably train your operators how to operate it, how to feed it, how to take stuff off of it, how to basically operate it. Maintenance tends to get very little training, or that's been my experience anyway. But I want to make sure that I have a robust training program. And again, all of this is meant to deliver the highest reliability and to make sure that the maintenance department has a fighting chance to maintain this very high level of reliability. So in that effort, years ago, I invented this process. And again, this is just how I run it. And if it adds some value to what you guys know and can do, that's very helpful. So here's that quote again: if you design something poorly, build it cheaply, and install it hastily, you don't have a world-class asset. You're gonna have a nightmare on your hands for a long time. But I need to show that design, build, and install. I need to show it algebraically. And the reason I want to do that is I want to show that anytime I increase an integer, D, B, or I, in this formula right here, anytime I can increase one of those, the overall result is an improvement. So this formula isn't calculating inherent reliability. It's not even calculating reliability of an asset, but what it does do is calculate my chance of having high reliability in an asset. Mr. Galati in his book uses for reliability. He uses I know it's a standard algebraic equation, but he uses minus or e raised to the minus. That's not what I want to do. E raised to the minus lambda, and then t being time. Lambda is 1 over mean time between failure and E is a natural log 2.71 or something like that. But this isn't a class on reliability per se. But so that's the formula. I'm not calculating in this formula reliability. That's Mr. Galati's formula over there for reliability. But what I am calculating is what are my odds? What are my chances of having a highly reliable asset? And so that's what I'm after with this DBI. So let's do a little bit of a case study. I need to see if I can move this screen out of my field of view here for a second. So here's a case study using this formula. I want to build, hang on a second, let me go back. Things never go as well as I plan, even my best intentions, projects that I've personally had to, ran from essentially a green field, building a new plant, or white paper, building a new piece of equipment. We likely set out to build the best machine possible, not initially considering the cost. After all, as a project manager, we should at least ask for what we want. I'm putting my project together. I'm building a brand new asset. I want standardization of parts. I want all this training. I want I want vibration isolation pads. I want circuit interruption. I want oversized cooling tower. I want all these things that are going to make my asset the best that it could possibly be. Our design, if we're doing it correctly, would hope to utilize parts we already have in our storeroom. That's the standardization of parts, right? Those are the parts that seem to survive in our environment. Why wouldn't we want to use those parts on our new machine, right? Because they're robust, our people know them, and we know how to troubleshoot them. That's the standardization. Our initial design might call for top shelf components. Let's get the most robust component out there. And I'd build it even in redundancy and self-diagnostic. I mean, my design would be really awesome. But there's concessions to be made, right? I can't have everything because we can't afford everything. So we've got to carve out and round out some of the features to fit it into our budget. This is that point I was making with the purchasing and the finance people. I mean, there's some realities to a business. This is what I want, but this is what I can get. And so I've got to make some concessions and some compromise. Even the idea of capital spare parts goes out the window. So my design, where I'd hoped that my design would be a 99%, out of 100, I end up with an 85%. So I've had to make some concessions based on budget, realities, practicality, whatever. I've dropped down to 85%. So that's the design part. So that's the D in my DBI. Now the building part, the B in my equation, doesn't fare much better. I'm forced to go to the lowest bidder. Again, I'm maybe not in conflict, but I have got to have agreements with how we purchase things. So, my company might have a rule that you got to go with the lowest bidder, and so that knocks us down a few percentage points. And we discovered during construction that the component that we actually wanted doesn't physically fit. So I've got to go with another model. So I don't get to use the part I want. I got to go with something that might be, less reliable maybe. And since we didn't specify the exact components we'd accept, we end up with whatever the OEM gets. This is an important part when you're dealing with an OEM. If you don't specify exactly what part you want, what components you want, the OEM is going to use whatever components they get the best deal on. So if you don't specify what is best for you, the OEM is very likely to pick the part they get the best deal on from their supplier. So this compromise on the build, because stuff doesn't fit, cost, what have you, or we didn't even specify it, we go from a 99 again, which is kind of a best case scenario, we get bumped down to an 82. So I had great intentions, I had a great design and all this stuff, and I ended up having to make concessions on build and on the design that bumped me down from a best case scenario, not to worst case, but less than ideal. The install is the end of the adventure. So we have to utilize, we're probably not building a new building for this machine. We have to utilize space that's kind of been cleared out. And so we do our best to kind of clean it up, cut back the utility stub ups. Someone has a cost saving idea of using the old disconnect. So even my power distribution, I got to use the old disconnect that's on the wall. I don't get to run new conductors. And the power distribution panel, I have to use the power panel too, and that saves about $1,000. So again, people are influencing my project that I didn't even consider, and now my installation percentage is being dropped down too. So earlier we had the bright idea to prepare the site with a vibration isolation pad, but we ran out of money. The cooling tower is a little undersized, but I think it'll work anyway. We had 2 weeks to install it, and many of you guys can recognize this scenario. You had 2 weeks to do the work, but the plant manager wants to run for 6 more days. And so now you don't have 14 days, you only got 8 days. So you got to sort of hurry up and get the job in. And so my install is dropping from a 99 to an 87%. So I had this great intention of having a 99% awesome design, a 99% highest possible build, and delivering an installation that would rate a 99%. But I've been sort of brought down by the reality of life to an 85, an 82, and an 87. And that nets a DBI of 61%. Now let me get, I should have, my numbers before of 99 times 99 times 99 would have netted a 97%. So my intention was to deliver an asset with the highest level of probable reliability, because I had the best design, I had the best build scheme, and I had the best installation intentions. But because of the reality, and again, most of you can recognize and identify with this, because of the realities of project management, we got to live within a budget and space and time. I'm down to 61%. Now, this would be a project that nobody really feels good about. Certainly as a project manager, I wanted to deliver better, but this is what we ended up with. And we're going to have a machine now that has, some concerns. It's not going to be a machine for the next 20 years. It's probably going to have some issues, because then again, we didn't build it and install it right. So where did it all go wrong? It went wrong. First of all, I would caution people, if we don't get the kind of machine that we want, if the number's not 97% or 95% or a higher number, I want the reason to be because we had to make concessions on cost, time, and space. Things that were forced into, the scope had to be shrunk. It wasn't because we didn't purposely want to design a good machine. We didn't purposely make efforts to build a good machine, and we didn't take the good engineering practices to install a machine properly. Let's not make ignorance the reason our score is so low. Let's not make ignorance and apathy the reason. If our number's low, it's explained away because, hey, that's business. You only have X number of dollars, and you got a space you got to fill, and you only got a certain amount of time. You can tie this into the rest of the plant. So let's see. I've got some hands raised. Let's see what we got. Good question. 26. Someone saying it's 61%. What do I got over here? Okay. PM development on my selfie, it will affect the equipment warranty. Oh, PM development by myself, yes. Let me address these questions real quick because they're good ones. Someone asked, does the PM development by myself, will it affect the equipment warranty? Yeah, and if I gloss past this, I apologize. I definitely take the OEM's recommendation of the things to check. What I was saying was, that's not the end of it. I also need to add to that. I was the chief engineer for a company that built fiberglass insulation ovens. So we built fiberglass insulation ovens, sold them all over the world. There's 1,600 companies in the world that use these things. And I can tell you from experience, as we're putting together the maintenance manuals, it's the very last thing that we do. And we're just simply taking cut sheets, or we did anyway, take cut sheets off of the components, and they don't match your operating context. And oftentimes they're very general. They might say something like, occasionally do this, frequently do this, from time to time. So it's not really defined. And so we're not eliminating the OEM's recommendations, because again, that would affect the warranty. But what we are doing is adding to that with a little bit more specificity. The 85, 82, and 87, that equals 61%, or that's at least the calculation I got. Also, somebody asked, and this is a good question too, shouldn't we take the average 85 plus 82 plus 87 and average that out? I've actually had clients, Ahmad, who wrote this in, I've actually had clients that do that. I'm simply suggesting, this is how I do it. I strongly suggest you take into consideration these three integers and come up, if a system of adding and taking an average works for you guys, I would be absolutely in support of that. I'm simply showing you what I do. Very smart question to take the average. If that works for you folks, I would strongly suggest that you do that. Again, just simply explaining my approach to this thing. So much of this can be improved, of course, and indeed guarded against by having a set of processes and procedures for capital projects. So what I recommend for my clients, and I'd recommend for you guys, is to think about the project as the best design, the best build scenario, and the best installation requirements. We can also give ourselves a better chance by having a set of component standards that we insist on. I think we get a better design if we have some confidence and assurances in the components that we recommend using. Now, one of my clients ran into this case, and it's very possible that you're working with an OEM and your company uses Allen Bradley PLCs. You guys are all about Allen Bradley. And the OEM, they use GE Fanuc on theirs. And you're saying, I'd like to have Allen Bradley because that's what we use. In this case, the OEM said, if we put Allen Bradley on this, it'll cost more money because we don't use Allen Bradley. But also, we can't guarantee the equipment will run properly with a different kind of control on it. And so I'm not sure what the client did with that, but that was a challenge that they were facing. So if I can use standardized parts, I have a high level of confidence in these parts. This not only helps the equipment design excellence, helps to store them out and helps the maintenance group to delivering higher maintainability. So there's a significant difference in what it'll cost and how many joules of human energy, quite frankly, will be needed to maintain an asset that comes to us with a 97% sort of rating on my little formula that I had versus a 61%, so 60.6 or 61. It's a different level. And so where do the values come from? I've got a blank slide here in a minute. Where do they come from? When companies want to adopt this practice or something along this sort of ideology, I ask them to come up with their own scale and to develop the scale. I actually, and quite frankly, in practice, it's very common for people to stay away from a percentage and maybe go more of a 1, 3, 5 or a not a high, medium, low, because I want something I can multiply by, but like a 20%, 40%, 60, 80, some not, because it's hard to distinguish between a 82 and an 83. So I need something that might be a little bit more definable for your organization, for your culture. So it's very customized, but I think I need to add some way to measure my ability to deliver high design, high build, and high installation. And so, usually 0 is worst case scenario. I'm just leaving it up to chance, and 100 is the best that it could ever be. Quite honestly, it's never 0, never 100%. It's somewhere in between. So it's really customizable. But the point is, whenever your organization says, okay, here's the system we're going to use, that becomes carved in stone. I even wrote carved in stone here. It becomes carved in stone, and that becomes the measuring stick against all your projects. You don't change the DBI interpretation depending on what you're building and installing. If you're putting in a brand new production press, like a big knuckle press that's going to press things or shape metal or something, that has the same DBI yardstick or meter stick, if you will, for a cooling tower or a new oven or conveyor system. This is how we measure our ability to deliver an asset that has high reliability, taking into consideration the design, build, and install of it. I'll get some questions here. Let's see what we got. You guys got some good questions. What is your recommendation, advice for the Allen Bradley versus XYZ situation? What do we need to take into consideration other than added cost by asking the OEM? That's a great question on the controls. I got to tell you guys, honestly, and this is just my 35 years of experience, if we don't specify the type of PLC we need, if we don't specify the type of variable frequency drive, if we don't specify all these things, electronic components, first of all, electronic components fail if you take in preventive maintenance optimization, PMO. and RCM, by the way, if you take those into consideration, electronic components fail in a category or a quadrant that's called sudden. That is to say, when an electronic component fails, it's very sudden to us. We don't have usually any sign that a little silicon chip on a circuit board in a slot in a door in a cabinet, we don't know that it's failing. So it fails very suddenly, or it seems to sudden to us, and it fails very randomly. That is to say, you never know when an electronic component's going to fail. There's so many things that can wipe one out. They don't last forever. So the danger of not having PLCs and variable frequency drives and other things that are sort of 4 to 20 milliamp, 1 and 0 type things is that my storeroom has to stock one of everything. If I don't have standardization of my controls, I end up with 3 different PLC brands and 7 different frequency drives in my storeroom. And I've got to have people that are trained how to hook a computer up to them, modify, bring timers in and out, modify the ladder logic. I've got to have more skills and talent on the maintenance side because I didn't standardize stuff. I'd say if it's just a cost issue, I would advise companies, if it's not out of the question, like $1 million, but you want to stick to a brand or type that you guys are familiar with and you have some knowledge around. But if the OEM is saying that we can't guarantee the performance of the machine without this type of controller, I don't see that you're left with many options. I don't see that you're left with many options. OEM stands for Original Equipment Manufacturer. And then somebody asked, how would you evaluate the expected life based on potential for 60 at a 61%? I'm hoping to answer that question a little bit more in this presentation, but I can tell you just from my experience, if I use that DBI formula, as I've stated, now the gentleman who recommended maybe taking an average and whatever process, again, works well for you guys, you guys might come up with a sort of a different answer to this, but my experience has been, and this is a page I left blank, if I do a calculation, and me personally in projects that I ran, using this DBI formula, it seemed to me that anytime I had a DBI result that was 60%, was less than or equal to 60%, I almost guaranteed myself that was going to be a very poorly performing piece of equipment. I was going to have a lot of operator trouble calls on it, and it was going to be a very difficult machine to maintain. That is to say, I would have a lot of chronic failures, a lot of things that repeat type failures, and I just couldn't quite put my finger on what the problem was. Anytime that formula comes out to 60 or below, it's a really troubling piece of equipment. And conversely, anytime that I had a 75% or above, and by the way, I would admit to you guys that was fairly rare to get that level of result. But whenever I did have something that I was confident was going to deliver that type of expected reliability, I had a pretty well-running machine. And again, it can't just be a calculation and 75 and I don't need to do anything else. I need to have spare parts. I need to have training. I need to have, operators know what they're doing, people not messing up the machine, that kinds of stuff. So I would say if you, now the gentleman who suggested that maybe taking an average, I don't know what numbers would factor for you, but when I do it as an algebraic formula, I find that these were the numbers, I had a sense that anytime it was below 60. So if I was kind of calculating something out was going to be below 60, I'd try to take a proactive approach and try to do something to either improve, wherever I could, improve the installation, maybe add in a little redundant air compressor off to the side, or whatever I could do that I thought I could sort of game the system a little bit. But I started out by talking inherent reliability and then got into this DBI. I want to leave you guys with the thought and the knowledge and at least the confidence that we're not the victims. We're not the victims of some random design. We have a say. Now, if our organization, if our companies don't allow us to be in on the design or the build or the install, at least to say have control over those, and we are truly left at somebody else's will, we're going to get whatever we get. But I want to challenge people to understand that the way the machine is built and the way that it's installed affect inherent reliability. And that's the most reliable it's going to be. And so how that ties into life cycles is if I get a piece of machinery installed and my company expects it to be performing at the highest level consistently for the next 20 years, and it comes in as a 45%, that isn't going to happen. It's going to be a nightmare, and maintenance is going to work themselves to death, and engineering is going to be coming up with all kinds of modifications to try to get it to last, and production is going to constantly say, we could produce the product if only a maintenance could fix that machine over there. It's going to be a nightmare for the next 25 years. I can almost guarantee it. So these are three very important characteristics to know about our equipment. I want to touch on the subject of full purchase price, and I'll get through this, and then we'll take a little break. The full purchase price is not the sticker price. Probably everyone on this phone call has gone and bought a car at some point, either a brand new car where you got a sticker. Again, I don't know where everybody's linking in from, but usually a new car has a sticker. It kind of tells you the gas mileage and delivery charges and all the different features and kind of what the car costs. That's not the total cost of the car, because it costs something to maintain that car and to operate it. And surely the fuel efficiency would give you some idea. But what happens is when we're having to choose between options of equipment and bids and quotes and things like that, the maintenance department, the engineering department may have one thought, and the other agencies that are very highly involved and engaged and really interested in the project as well, operations, procurement, safety, environment, these other folks, they're looking at a different number. And sometimes the number that we're looking at isn't the full purchase price. We know in maintenance and engineering, we know that there's more to the cost than just what it costs to buy it and deliver it. There's the operating cost. And this is information we can actually find out. This is information that we know, especially if we have a standardization of parts policy, because we know how long those components last, because we know how to take care of them. We can essentially anticipate the mean time between failure. So are we just making asset acquisitions based on the initial cost? If so, that might not be telling the whole story. So I've got to buy a machining center. I've got a mega turn, a speedy turn, a econo turn, and a maxi turn. And by the way, this information is sourced from North Carolina State University, that college program, their program. It's a great example of this illustration. I've got 4 machines here. Which one of those do you think we're likely to buy? If those are the 4 quotes, there's a good chance that we're probably going to be encouraged to buy this one right here, simply because the cost is the lowest. It's the econo turn, after all, economy, right? It's smart buy. It's only $450,000. We're probably not going to buy this one. It's way too much money. So we've got to make, we've got to make a decision which one's buying. And if that's all the information we have, we're very likely to make a premature decision. No, so somebody's asking total cost of ownership. No, and this, we're going to build up to that, but this is simply the purchase price. How much is it going to cost? Like buying a car. That car's $40,000. I'll buy that car because it's the least expensive car on the lot. Someone also wrote, mostly as an OEM project, we would be involved mainly in installation and commissioning. So you've got the commissioning, certification, and startup steps. I include that in the installation. In my little formula, I include that as part of that, what the cost is. Or what, if I've got a good commissioning program set up, I'm likely to have good training. I'm likely to have good understanding of the equipment, theory of operation, that kind of stuff. So kind of staying with this, this example of full purchase price. So here's all the information I have. Probably the purchasing department, procurement, probably plant ownership, the CEO, CFO, people that are on the money side of it are going to say, well, let's buy the $450,000 one because then we have extra money to do other stuff. So I might have external pressure on me as a project engineer to go with something that I just don't have a really good feeling about. I probably would ask other kinds of questions around this, but if I'm being pressured by other agencies in my own company to buy something different, or do something different, I might make a bad decision. Someone wrote in, but the low cost machine might also be less effective. Yeah, that's exactly the point. But then again, I mean, it really could be the best machine. It just happens to be the least expensive one. Now, if we add more information to our decision, now we're taking a look at first year operating cost. So where the Econoturn was my best deal initially with just 1 year of data. So if I was to work with the OEM and come to understand what's the expected maintenance costs and what are the spare parts you're recommending, operation tooling, setup, and training, I could factor in. And by the way, if you ask the OEM these questions, they're pretty much going to share it with you. Well, based on our experience and other machines we've built, here's kind of the cost that you would typically see. So I've got 1 year. So still the Econoturn looks like a pretty attractive machine. So again, we're being, with all things being equal, we're being pressured, and we're probably starting to think too, well, okay, that looks like the least expensive machine to operate. So that's probably our best choice. But if we're able to project 3 years out and even 5 years out, we're likely to have a different picture. So if we look 5 years out into this machine and we're able to project, again, we've got standardization of parts. We know how much money we're going to spend on training and tooling, that kind of stuff. The Econoturn now turns out to be the most expensive machine to operate, even though it was the least costly machine to buy. And what becomes most attractive now is this MaxiTurn down here at the bottom. And it was another $100,000 to buy. And the point I'm illustrating here is I've got to make an argument at the beginning of this whole project to the procurement department and to the leadership of the organization to allow me to spend an extra $100,000 of today's money to buy a machine that I'm projecting is going to cost less to maintain, less cost of ownership in the long haul, or certainly over the next 5 years. And I'm better able to make that argument. I'm better able to make that argument if I can show them facts and figures and information. Somebody wrote in, how do we get this information? The OEM will share whatever information they have and they can share with you. If I'm using, again, this position of standardization of parts, I know how long a 25 horsepower motor will run. I know how long a Rexroth cylinder will run. I know how long my IO cards and my Allen Bradley PLCs will run because I know how to take care of them. I know how to inspect them. So I have a real good sense about how often I need to replace these things. You could also look, and this is a little bit more on, this is a little bit more FMEA, so it's not so much part of this discussion. But I know that if I buy a 25 horsepower Baldor motor, I know it's got a service life of 20,000 continuous hours. So if I'm running that thing continuously, I know that that's an average now. It doesn't mean it's going to die at 20,000 hours, but I know that I have a sort of a range by which I need to replace that motor. So in 5 years, I know I need to replace that motor 6 times in 5 years. So I know the cost of that. So it's oftentimes knowing the cycle life, the duty cycle of my components, not every component, like buttons and handles and things, but the major components, the motors, the drive system, essentially, how long is that going to last? And you can make some assumptions. And by the way, if you're using these numbers to compel leadership and finance to see it your way, make sure you're telling them that the numbers are your assumptions. I'm not just making up numbers to make my selection more attractive. I'm actually, scientific as I can, I'm making some assumptions. Somebody's asking if quality and effectiveness matter. Yeah, that's the whole DBI thing. CapEx low or CapEx or OpEx high. Yeah, so there's capital expenditures. Hey, by the way, if the company's willing to pony up a lot of money on the capital expense and our capital expenditures, and it's not coming out of my budget, I'm all for buying the most expensive machine. What I'm really interested in is the cost of ownership. How much is this monstrous machine going to cost me to maintain over the 20 years? So these are the CapEx is that somebody's asking, are they CapEx or OpEx? The CapEx is the number, the purchasing price. All the other numbers are operational expenses. And then also running style, of course, factors. So again, this is just I'm trying to use number projections, cost projections to sway an argument over buying one machine or the other. I've got to get the machine that's the most reliable. I got to get a machine that is the least costly, that that is a better machine because I'm going to have this for 20 years. And the cost of ownership, if I've got a very bad machine, because it was attractive to buy it because it was cheap, but I bought a bad machine because it's going to be very expensive. In the long run, I'm going to be losing money. I'm going to be losing some money. So here's what that looks like kind of graphically. How often do we project or determine future costs when considering purchases? I got to tell you, when I started out in a professional career, I didn't have a concept about future costs, so I didn't personally do it. But as I got a little smarter and got a little bit more responsibility, I tried to project as many costs as I could. Was I always right? Nah, probably I was not right very often at all, but I was certainly in the range of a reasonable, plus or minus maybe 25, 30%. So you get pretty good at this estimates. And again, if we got standardization of parts, we're likely to hit around equipment. We're likely to hit around the numbers that are probably right. What I'd like to do now is take, I see we're a little bit past the hour. Let's take 5 minutes if you guys don't mind. I'm gonna mute my mic, but I'll leave my camera on. Let's just take 5 minutes and I'll see you guys in 5. Okay, guys, I'm back. Someone had put on the chat if there was a chance to that LEORON would host this training again, that they had kind of gotten short notice to get on it, and some of his colleagues would like to attend as well. I'll work with LEORON to make sure that we can make that happen. Again, I think it's a timely discussion, and we want to facilitate as many people. If this is helpful and knowledgeable, again, I'm sharing with you my experience, and I may not have answers to all your questions. I'm just giving you some of the design things that I've created, or at least that I employ, and how I do things. So just to kind of recap where we were, we started out talking about inherent reliability. Assets come to us with reliability. Engineers are responsible to deliver the best product possible. Maintenance is responsible to keep it up, and keep the inherent reliability in. I use a formula, DBI, design, build, and install. It just helps me understand the major categories that affect the ultimate reliability of my chances of having a piece of equipment that I think is going to be reliable. And we talked about the full purchase price. That's kind of where we ended. That everyone, I've got to tell you guys, my experience has been everyone in the organization that's not in maintenance and engineering is going to be looking for you to, that's why they ask for bids. They're looking to purchase the least expensive, the cheapest, if you will, machine that can be bought. But we know in maintenance, because we're the ones that are going to have to live with this thing for 20 years. We're the ones that get called out at 2 o'clock in the morning. And in engineering, it's our professional stamp on this machine that it's going to be a good, viable machine. That to just look at the sticker price, just to look at the initial cost, or the CapEx, as someone would say, it's not the full story. I want to get as much information up into including, and I don't know if this is even possible. It isn't pharmaceutical. It's possible in oil and gas. It's possible in a lot of meat processing plants, to go to other customers of that OEM and ask them what their experience has been with the piece of equipment, and you can get some idea what the cost is if they're willing to share the information. A lot of that is proprietary because you're a competing organization. So, whatever's possible, I want to get this information. And sometimes I just have to make a wild assumption, but I want to be very clear and transparent and honest when my numbers are factual and when my numbers are just sort of a scientific guess, if you will. The last part of this section is what we're dealing with sometimes is people that think the point is inexpensive does not mean cheap. I want to buy an inexpensive car. I want to live in an inexpensive house, but I don't want a cheap car, and I don't want a cheap house. I want to buy inexpensive clothes, but I don't want cheap clothes. But some people think they mean the same thing, that they're synonymous with each other. There's a popular saying, and I don't know if it's popular where you guys are geographically located or in your culture, but it's stepping over a dollar to save a dime. People will go out of their way to pick up a dime off of the ground, 10 cents, but they won't do the kinds of things that will improve their means by a dollar. For example, I will drive all over town looking for the cheapest gas, the cheapest gasoline for my car, not realizing that I just drove all over town looking for the cheapest gas. Had I just bought the gas at the gas station next to my house, I would have saved myself all the money from driving around. But I think I'm getting a good deal because I saved a couple pennies on a tank of gas, or on a gallon of gas. Unfortunately, we don't always take into account the full cost of buying cheap components. Cheap means poor quality. Let's get the terms right. Cheap means it's a poor quality. Inexpensive means that you bought it for a good price. We got a good deal on it. So I want to invest in things and buy things that are inexpensive. I don't want to buy things that are cheap. And here's an example. I've got two seals here, Vega seal and a Duraseal. And this again comes from Marshall Institute out of their program, their TPM program. I've got a seal that costs $20. I got one that costs $60. First of all, if that's all the information we had, probably everybody on the call here would buy the $20 seal because it's the least expensive. But when I look at the Vega seal, it lasts 1 year, and the Duraseal, it lasts 2 years. I still have a ratio of $20 a year versus 30. So if that's all the knowledge that I have, if that's all that I know about this seal, I'm still going to go with the Vega seal. But you guys do know there's a catch to this story, right? When I take into consideration the cost of replacing the seal, and the Vega seal has to be replaced every year at $75, that's my labor cost, that now becomes a prospect that's cost $190 versus the Duraseal, which at $75 installation lasts 2 years, is only going to cost $135. So once I get past this, thinking cheap is a good deal, cheap is a quality, I start to realize even though the Duraseal was more expensive initially, it lasts longer, and the ultimate overall cost of having that seal is $135. What's likely to happen if I go just off of cost thinking the cheap is the best deal, I'm likely to find myself replacing a lot of seals every year because they only last 1 year. And in fact, because my organization might not be very good at maintenance in general, I'm probably replacing that seal more often than once a year. Maybe I'm replacing it 1.5 times on average per year. So what we have to do, if we have to, now we have to do the kinds of things that make that Duraseal last for 2 years. So I went with not the cheapest seal, I went with the one that was the least expensive, the Duraseal. But it's only advantageous and it only becomes a positive if I do the good maintenance that causes that seal to last for 2 years. I've got to, the things I got to do to ensure that it lasts for 2 years is the spare seal in the storeroom. I got to store it properly. That is to say, if it's affected by heat or humidity or sunlight, like if it's got a rubber and UV light on it, I got to guard it. If it's a mechanical seal, if that's what we're talking about, I got to guard against the vibration of the shelves. I don't want to put it on a metal shelf. I got to store it in the box and the wrapping it comes with. I've got to protect it in the storeroom. So when I put it in, it'll last, it's got a chance of lasting for 2 years. I have to install it properly. I've got to line it possibly. I can't have like misaligned seals, and so now I'm getting blow by or I'm getting leakage or something like that. So I've got to install it properly, and whatever else it goes, whatever kind of seal we're dealing with, I got to do the prescribed good maintenance practices that allow for the seal to last for 2 years, because that's where I make my money. It lasts for 2 years versus 1 year on the other one. So cheap and inexpensive are not the same thing. I want things that are inexpensive to buy and to maintain. I don't want cheap things to buy because they are usually very expensive to maintain. And the seal is an example. I've got to replace it every year. There's a cost, not just the cost of labor, but there's a cost of other stuff I'm not getting done because my mechanic's over here replacing the seal every year. He or she is not doing other kinds of activities that a mechanic could be up to. So that's a discussion on design, build, and install. And what that's meant to do is to give me the highest level of probability of delivering and putting into production a machine that has the highest level of reliability that we could possibly control. I've designed it the best I could and allowed to do with the cost and the time and stuff. I built it the best I could with time and cost, and I've installed it as best I could using good engineering practices. I picked the machine. I chose the vendor and I chose the machine that didn't have the least expensive purchase price per se, but had the least operating costs that in the long run costs less to own, cost of ownership. And then I took into mind or kept in my mind that I want components that are inexpensive and not cheap. Inexpensive because they last longer, but it only plays out if I do the kinds of things that make that component or allow that component to live out their natural life. If I buy a more expensive motor because it lasts longer and I treat it like the rest of my motors and I have poor maintenance practices, that brand new motor is not going to last any longer. The better motor is not going to last any longer than the regular motors. So I got to have some good maintenance, good manufacturing practices going in my favor. let's look at Mr. Galati's tables and corresponding curves. Again, my friend Terry back in 1986 was broaching the subject. He's the one that mentioned this to me. We didn't know about, Mr. Galati hadn't written his book yet. I was not much of a student in this. I was just starting out my professional career. I'd only been sort of out of college for a year, so I really didn't even know what I was talking about. But when Terry was talking to me about this, I always kept that in my mind because I thought it was such an interesting approach to things. And then years and years and decades later, I become a student of this myself, and I read Mr. Galati's book, and I've actually met with him. I've not talked about this particular subject with him, but I've met him a few times, and I'm just really impressed with this. And this is an approach that I take. I don't work for a company anymore. I'm a consultant, so I don't do this in my own plant per se. But this is what I consult with and work with my clients. And I did a little bit of this myself, but again, just in the very early stages because I was just kind of understanding it myself. But first of all, as I mentioned before, Mr. Galati's book, Maintenance and Reliability Best Practices, if you're a professional in this space, I strongly recommend that you purchase or have on your library the seminal book by Mr. Galati. I think it's just a great addition to a professional library. In this book, he provides guidance for the breakout of life cycle cost, and they're represented in two specific graphs. In fact, they're tables, they're not graphs. One is for the Department of Defense. So Mr. Galati himself is the chief, I'm not going to get his title right. He's the chief designer or he's the chief engineer, but he's somewhere high in the engineering in the Department of Defense. So he's in the U.S. Department of Defense. He works, and I don't know exactly where he does work, but I know that he's in that sort of industry. And then he has another table for just general industry. So he's got some ranges of things, and I've made some interpretation of these, and I just want to show you guys what I do and how I do this. This is essentially the life cycle costing assumptions. So first of all, Mr. Galati in the Department of Defense costing, here's what his table says. He says, for the life cycle cost of an asset, so this is the Department of Defense, so you can think airplanes or tanks or howitzers or jeeps or anything that would be a military type thing, a piece of equipment. The design and development cost of that asset should reflect 10 to 20% of the overall life cycle cost. So whatever we spend on design and development would represent about 10 to 20% of the overall life cycle cost. Of course, that cost is in the life cycle cost. The installation of it, and for the gentleman that was asking about commissioning and validation and startup, the installation, commissioning, validation, startup, all of that would represent about 20 to 30% of the overall life cycle cost. So if you look at just the high end of those two ranges, we've already spent 50% of the life cycle cost before we even turn the machine on. Operations and maintenance will probably cover a range about 50 to 70% of the life cycle cost. And there's always a cost of getting rid of stuff. I've got to, at some point, I've got to take the old press out or the old tank, cut it out of the ground basically, and get rid of it. And there's a cost to that because there's a cost for disposal of solid waste. Many of you folks that are listening in, you're probably dealing with highly hazardous chemicals or elements like mercury switches, or you might have some radioactive equipment that might be in metal detectors and things like that. So there's a cost of getting rid of stuff. You don't just chop it up and throw it in the furnace and melt it down or throw it over the neighbor's fence. There's a cost of disposal, and it usually represents 5% or less of the overall life cycle cost. So I don't spend too much money on that. So for the general industry life cycle costing, the spread is a little bit different. Hang on a sec, I got a question here. Oh, someone's saying they can't see the tables. Chris, I don't know if you're still on the line or not, but apparently some people can't see my screen. So if you're on the line still, can anyone see the tables that I'm showing? I didn't do anything since I've been gone. Let's see if somebody's responding to me. Okay, so some people can see it. That's good. The question was, what are the basis for these tables? Again, I have not talked to Mr. Galati myself. I don't know his source for these. I don't believe that he just made them up. I don't think that's the case. I think his information is probably pretty solid. He does work for the Department of Defense, so he may very well be in the know on that part of it. He may be in on that part of the department, the procurement side of it. I don't know for a fact. I will tell you though, I'm hope to see him in October at the SMRP annual conference in Columbus, Ohio. If I do see him, I'm going to bring my book so he'll sign it. And I'm also going to ask, I will ask and endeavor to learn where these charts came from. And they are very interesting, and they are ones that I have found to be very useful. If for nothing else, at least it gives us a foundation of what to expect. And so for general industry, so I'll just go back real quickly to the previous slide. That was Department of Defense, and you'll notice the range here of estimated cost. For general industry, it's just a little bit different. It still ranges in those categories and just a little bit different. And what I've done was I've taken Mr. Galati's tables, and you can see those on my screen. They're in the upper right-hand side. This is Department of Defense. So I just sort of copied that over. And I built a life cycle curve using the factors in his table. So he says the design, development, and installation are what I call the DBI. He says that should be a range of anywhere from 30 to 50%. So you gotta sort of add these two together. That the disposal cost, let's just say it's 5%. That leaves anywhere from 50 to 70% for my operating life cycle cost. What's interesting about this discussion is when I get a asset, when I get it purchased and I get it installed, whatever that number is, I can determine how much money I intend to spend for the rest of the life of that piece of equipment, because it'll be reflected in this percentage. And I'll show you that. I'll show you guys that in a scenario in just a few minutes. Likewise, I've taken the curve for general industry. This is the table again that Mr. Galati has in his book. And I've built a similar life cycle curve that tells me where my costs are going to be. Anywhere from 50 to 30% on the design, development, and install. 5% again on the disposal. We'll just use that as a constant. And then operating costs will be anywhere from 65 to 85% of the total life cycle cost of ownership of the whole thing. So using Mr. Galati's, Ramesh's work, kind of backwards engineered what these graphs might look like, and that's what I've come up with. So now when I'm consulting with companies, working with them to decide how much more life they have in a piece of equipment, I'm asking for what it costs to buy, to build, what it costs to deliver it and install it and get it operational. And then I can factor in what a disposal cost would be. And then I tell you how much money you probably have in the lifetime of that machine to spend. And again, I'll show you this at the end of the presentation and the scenarios that we have set up. So the control activities along that life cycle curve, this is the stuff that maintenance actually does. And control activities is a term out of ISO 55000 asset management standard, if some of you guys are familiar with that. Maintenance only has a couple of options. I mean, in the scheme of things, maintenance really only has a few things that we can do. We can run to failure, emergency work, or EM, you might call it. We can do corrective maintenance. Again, it's only a finite number of things that we could do. We can do preventive maintenance, and inside of preventive maintenance, there's 7 different types of preventive maintenance. There's servicing, like a good example would be if you're going on a trip in your family car and you're taking your family on a long trip somewhere, you're going to put air in the tires. You'll probably vacuum and clean out the car. You might wash it. You put, you'll check the radiator fluid. You'll check the washer fluid, check the air filter. You'll do a couple things, kind of servicing kinds of things. Another type of preventive maintenance is installation and replacement. This would be like an air filter or something like that, oil filter, that you replace on a hard set time. Calibration is a type of preventive maintenance. So is alignment and adjustment. Inspection is probably the one that we're most familiar with, a PM that's an inspection. Check the belt, check the bearing, check the cylinder, these kinds of things. The most important preventive maintenance task that we have is lubrication. And so that makes lubrication the most important PM. And so these are one of our options is do preventive maintenance, and it's usually one of these 7 things. The other option we have is to do predictive maintenance. And I just wrote, there's all kinds of predictive maintenance. I just wrote down the more common ones. And most of you guys probably adhere to these: vibration analysis, infrared, oil analysis, or ultrasonic inspection. So in the scheme of things, for the control activities, the thing that maintenance does, and remember, we're doing these things to guard the inherent reliability. So we got to do the right PMs at the right time. We got to align things properly. We got to torque things properly. We got to lubricate things properly. If we do anything less than the right way, we're probably affecting the life of the equipment. So someone's asking, considering the U.S. defense is having the highest budget across the globe, yeah, that's actually true. Shall we consider their estimated cost as a reference? Yeah, all of this is a reference. It's again, I've not talked to Mr. Galati himself. I've just taken this at what he wrote. It's a range, you know. And then someone asks, is DBI factor changed? As the DBI factor changed, will it affect the cycle shape? I think if I have, what my experience has been, if I have, again, using DBI, and it's really a formula I came up with, so it might only be relevant to me, but I use it quite extensively. If I have a high probability for reliability, I find that as the equipment gets older, I'm not spending more money on it. I've got a real predictable amount of money I spend. It's a routine. One year looks like the next because I don't have emergencies. I have a very well-designed machine, built very well, installed really well. And on the commission, validation, and startup, the CVS, the one gentleman asked about, I've trained my people. I've got the right spare parts. I've got all that going. So I've got a machine that is very straightforward to maintain. There's not a lot of surprises. It's just an old, reliable piece of equipment. So it'll be at the very long end. As a matter of fact, let me just go back because that's such a great question. I would see that this is life cycle for general industry. I would see on a machine that has a very high DBI, I would see that the operating life would be 85% of my cost at the very high end. I built a machine very cost effectively, but I got an awesome machine, and I'm able to spend the money, maintain M&R cost over the lifetime of the machine. So just whoever asked that question, just really a brilliant question, and thanks for asking that. So I want to show the control activities on the life cycle curve. So in this example, I've got just as an example, I've got a machine that has I'm going to depreciate over 10 years. So I've got essentially 10, my lines aren't very straight and I apologize. I've got sort of 10 years to look at this machine. But what am I doing to that machine? I guess there's another one right here. What am I doing with that machine year in and year out, day in and day out, month in and month out? I'm doing the same stuff. I'm doing preventive maintenance. I'm doing predictive maintenance. I'm doing corrective maintenance and emergency maintenance. Every now and again, this is very predictable in the sense that a good engineer, a good engineering department, a good well-designed machine, maybe every other year, maybe every other year, if you will, I've got to do some sort of upgrade, or there's something, like an upgrade, if you will, to, it needs an overhaul. Or maybe every year you shut it down, replace all the belts and tighten everything and grease things you can't get to. So there's some annual and semi-annual kinds of things. But for the most part, we're just doing preventive maintenance and predictive and corrective. And again, these have to be the right, and we got to do them purposely and with good maintenance practices to get an awesome result. So I'm delivering the value. Somebody asked about the resale price, and that's a great question because I'm also teaching. LEORON has a great course. By the way, when I say great, I mean this is a fantastic course. They've got a course going on about asset management. It's on ISO 55000, and just a great group of professionals in that class asking really great questions. And one of the concepts is that an asset has value to your company, but when you no longer have use for it, if we've taken care of it, if we've done the kinds of things that ensure it's still a valuable piece of equipment, it has a higher resale value. So in asset management, the value of an asset doesn't end when you're done with it. It has value to another company, but only if we've maintained it at the highest level. So the gentleman, or the person that asked that question, that's a great question. The resale value is improved if I've got clear objective evidence that I've taken care of the machine over the time that it's been in my facility. Kind of like your car. It's got a higher resale value if it's evidence that you've actually taken care of it. So here's a question. The operator cost relies on the selection, the operation cost relies on the selection of design team of the contractor who's looking for the cheapest solution. Yeah, again, the contractor's going to cut costs because they got to protect their margin to deliver and handover. How do you control this? That's controlled in the scope of work, and that's something. And again, I don't mean to implicate engineers. I'm one myself, but it's the scope of a project. Sometimes we've gotten I wouldn't say lazy, but we've kind of gone on autopilot. We've got to really define the scope of work and to be in system on what it is that we anticipate and we expect. Because if we don't, an OEM, I mean, you'd do the same thing if it was you. An OEM is going to look for ways to cut costs and save money because I'm trying to protect a margin. I put a bid in to do the job at a margin that I thought that would be acceptable, and I want to get the bid. And as you guys know, on those that are engineers and run projects, contractors love changes. They love scope changes because that gives them a higher profit margin when we start changing the scope of work. So also someone wrote in, please define estimate of the useful life cycle of an asset. And if an asset machine is troublesome, out of luck, when will we be replaced? I'm going to talk about that at the end in a scenario. How can we define estimate the useful life of an asset? Well, this is what's projected, and this is I don't want to get too much into the weeds on asset management, but let's have a little discussion about that. On asset management, the company or the organization is going to buy a machine. They expect that machine to produce a product or to provide a service, or essentially to add value to the company. We're buying this new press. We expect the press to be here for 10 years. We expect it to cycle, run 5 days a week, 24 hours a day for 5 days. It's got a cycle time of every 30 seconds. It's a big knuckle press, maybe every 20 seconds. We expect it to do this. You can have it on the weekends for maintenance. I have an expected cycle runtime on it. I have an anticipated cost of ownership, raw materials and lubricants and hydraulic fluid and all the things, that go into that. And I expect that machine to be performing 10 years from now. The company bought the machine, the asset, expecting it to perform at that level for 10 years. And it's, again, if we bought the right machine and we maintain it properly, it will be here for 10 years. It's not supposed to go, its value doesn't depreciate. I mean, its value on the books depreciate, but its value to the organization is not supposed to depreciate. When we start thinking, the age of the equipment has nothing to do with the value of the equipment. If we don't pay attention to the degradation of the equipment, if we let the equipment start degrading, now age has everything to do with it. Somebody's asking about the best maintenance types. I'm just demonstrating that this is real, in the scheme of things, maintenance really just has a limited number of things we can do. And if you notice, we do the same thing month in, month out, year in and year out. We do preventive maintenance, predictive, corrective, emergency work. We do some overhauls. There might be some modification because now we want the machine to run to make a different product. So we got to modify the RAM or the hydraulic system. I need to add a hydraulic cooler to it because I'm running it more often. There's things that we do. That's sort of life of the equipment. But ultimately, I'm expecting this asset to be around, in this case, for 10 years. And these are the things I'm going to do to make sure that it's providing value. That life cycle curve isn't meant to show that the machine is degrading. It's just the curve of time, basically. It's not showing the equipment's got less value. But speaking of value, and this is out of asset management, under the auspices of 55,000, that's the ISO standard, companies are required to periodically, and I would read that as annually at least, assess their systems and measure if their assets are returning value. first of all, if we built a poor machine to begin with, or even a good machine, and we're maintaining it poorly, the machine at the end of 10 years, we perceive it as less valuable because we didn't maintain it. As a matter of fact, it doesn't even take 10 years, probably in a brand new machine that's designed poorly, or a brand new machine that we haven't maintained very well. In about a year's time, we don't even recognize the machine. So it's running so poorly. We haven't done anything to ensure it. So we have to do on at least an annual basis. Again, if you're an ISO 55000 certified company, you're required to do this at least annually, is take a look at the asset and ask yourself, is it still performing like we thought it would? Have we spent the amount of money we thought we would? Does it still have the remaining life that we thought it would? If an organization can keep track of the life cycle cost of their asset, they can determine if there's enough value in the asset, enough value in the asset compared to how much money I have in the bank to maintain it. And I want you guys just to keep that thought, because I'm going to bring that into a scenario at the end. I think that'll tie it all together. Every year I can take a look and say, do I have enough value left in this machine compared to how much money I have in the bank to maintain it? And so here's that. I'm just demonstrating that every year we're checking on the asset health, and whatever that checklist looks like for you guys. The ISO standard doesn't specify what you'll do. It'll just specifies that you do it. I bought this machine. It was to deliver this value to the company. When that could be production rate. That could be production, first pass yield, high quality, production. Am I still getting that on year 7? And if the answer is no, and I have spent a lot of money and I'm getting to a poorly performing piece of equipment, I got a business decision to make about that piece of equipment. Maybe I need to cut my losses and buy a new piece of equipment. Maybe I need to take some look at injecting a bunch of cash and modification to it to kind of shore it up a little bit so it'll last another 3 years. But I need to make this asset health check, and that is a requirement for companies that are following asset management. So in the category of spare parts, and if you recall me mentioning, I think at the beginning of this session, I think in the United States anyway, this is the Achilles heel. This understanding of what parts we need, access to spare parts, acquiring those, the logistics chain required, lack of standardization of parts, and just simply not many people knowing what they're doing, quite honestly, is affecting our ability to have a really good spare parts program. Suppliers over time increase the spare parts price to force operators to go to the new product printers. Yeah, look, I don't know who's on the phone in terms of OEMs or suppliers or anything. Again, this is just my 3 decades of experience, but spare parts suppliers, their advice and their assistance, it has to be measured and evaluated, because you're dealing with people who make more money the more they sell to you. And so take that for what it's worth, but it's got to be, we've got to be driving this thing. We can't be left to somebody else's devices. So what's wrong with this picture? This is a storeroom. This is a storeroom that has nothing on the shelf. And my question when I'm teaching, this comes out of a class I teach, is what's wrong with this picture? And usually I'm talking to storeroom people or maintenance managers. And they say, well, what's wrong with this picture? Is there's nothing on the shelf. It's an empty storeroom. Oh, before I get into the storeroom, somebody asked a really great question. How to account when the operating condition changes in the middle, which impacts asset performance, in turn higher maintenance cost. Yeah, that's another, boy, you guys are sharp. That's another brilliant question. The way you do that is you have a process by which I anticipate that happening. I anticipate we're going to make a different product than it was designed. We're going to run it out of the design parameters. We're going to run it longer. We're going to make a different part. We're not going to do preventive maintenance like we thought we would. We're not going to take the machine down. All the things that changes the operating environment that it is. I would have a policy or procedure. Here's how we're going to handle it. We're going to agree that we're going to make asset-based decisions. We're going to shorten the anticipated valuable life of it, or we're going to run out of money faster than we thought we would. but at least know that if you change the context, the operating environment, the context of what the machine was designed to do, you're affecting the longevity of it. You're probably not making it longer lasting. You're probably shortening the life, and you're definitely affecting how much money you anticipate spending on it. You're not going to spend less money on it, not typically if we're modifying it to get more out of it, not for the purpose of reliability. So the answer to this question is, what's wrong with this picture? The answer, quite honestly, is nothing. There's no need to have anything in your storeroom at all. What happens is maintenance and engineering and plants and organizations think that I got to have a storeroom full of spare parts. And the truth is, I end up with a lot of spare parts that I just end up mismanaging, because a lot of them become obsolete. A lot of them degrade and become damaged, quite frankly, in the storeroom because of poor handling and poor storeroom practices. I don't really need a spare part until the moment I need it. If I went to a grocery store to buy a loaf of bread and there was absolutely nothing in the grocery store except for a loaf of bread, I would be a perfectly satisfied customer. I went in for a loaf of bread, I got the loaf of bread, and that ended the transaction. There's nothing wrong with the storeroom that doesn't have anything. The storeroom just needs to be able to get everything I need when I need it. And for some reason, over the centuries, I guess, we've gotten into our mind that we have to have a storeroom stocked with something. And we end up making bad decisions on what to stock, and we don't have any rhyme or reason, and there's no standardization of parts, and pretty soon we're buying a lot of stuff and we're mismanaging it. In fact, we oftentimes can't find what we've got in our storeroom, and we end up having to fly parts in, expedite parts in. Here's some sobering numbers. I want you guys just to soak this up for a second. It's not unusual for up to 30% of a company's expenses to be equipment reliability related. So whatever the expenditures are for your company, your facility, it would not be unusual for 30% of those to have some reliability connotation around them. And up to 40% of that 30% is just in spare parts. Now, in the United States alone, the spare part industry is $150 billion. I don't know what that translates to anybody's local currency, but I can tell you that is a whole lot of money. Many organizations find that up to 60%, and this number comes from Honeywell, it might come from Rockwell, but it comes from one of those organizations that says their experience is that 60% of US manufacturing plant inventory is obsolete. That is to say, that part doesn't go to anything in the factory, or the part is in excess to what they actually ever will use. These are parts that have no value. I mean, imagine that. Imagine you had a storeroom, in your maintenance storeroom, you had $1 million worth of stuff in there. Now, that's a very small storeroom, by the way. But let's say you had $1 million. If you use this Honeywell or Rockwell, I forget the source, I apologize. If you use their number, that means that up to $600,000 worth of your inventory could have no value whatsoever to your operation. So you have a storeroom that's stocked full of stuff, but nobody wants it and nobody needs it. Simply stated, we don't have good maintenance storeroom processes. Our people in our storerooms are probably awesome, great people. They're great humans. They're trying to do a good job, but we probably have very bad processes. Let me answer some questions that have come in. Let me see what those are, if they're relevant to the subject at hand here. Oh yeah, so a couple of great questions. Empty storeroom means storage capacity if not utilized. Okay, I get that. Should the store have a reliability engineer full time? I don't know if the storeroom needs a reliability engineer, but I can tell you, I would be insistent as a plant engineer. I'd be insistent on having a reliability engineer, and that reliability engineer's function is two things: increase mean time between failure and decrease mean time to repair. And that's what my reliability engineer should be doing all the time. Here's a question or a point here. We should have at least the items required for emergency cases as will be practiced. Yeah, I absolutely agree. And my point is that we have to make smart decisions on what to stock. In fact, a storeroom should have, if you guys are familiar with a term called turn rate, I want my, the world-class number for turn rate through the A.T. Kearney study is 1.4, which means my storeroom doesn't turn very often. There's very few things in it. I mean, there's very few value to it. It's just for emergencies. When I'm setting up storerooms around the world, I'm looking for my clients to have a turn rate of 2.3 to 3.4. because I want us to have enough stuff to get by these emergencies. And when we have really awesome preventive and predictive maintenance and really fantastic planning and scheduling, then in a very controlled fashion, I can start bringing my inventory value down to just those emergency items because we don't have any emergencies. We prevent and predict almost everything, and we plan and schedule all of our maintenance. But I want to start out at 2.3 to 3.4 and I have to have really good preventive, predictive, and really good planning and scheduling. If I don't have that and I try to reduce my storeroom inventory, I'm going to have a lot of stockouts and emergency purchases. So the last point on the slide I think is a key one. Spare parts begin and end with an asset's bill of material. And I hope that you guys will remember from before the break, earlier in the conversation, I talked about that one of the things we have to demand from the OEM is a bill of materials. And I even said in English and in writing and electronically. And it's an engineer's responsibility, it's the project engineer's responsibility, quite honestly, to bring this bill of materials into the factory. Now, once it comes into the plant, the person who's in charge now of keeping the bill of materials up to date, the person who's actually responsible for that is the maintenance planner. The engineer just brings it in, gives it to the planner, it gets put in the CMMS and the asset register, and the planner is now responsible to keep the bill of materials up to date over the 20 years, the 10 years that the asset's going to be here. But it starts with that bill of materials. A lot of us were exposed, again, I apologize, I don't have a listing of where people are geographically, but here in the States, our exposure to a bill of materials as we were younger was the car catalogs, these Chilton magazines, there was a brand of them, and they basically had exploded view diagrams. So it's very common that you guys would have an owner's manual or equipment manuals for your equipment, and what you have as a bill of material is an exploded view diagram. It takes like a engine block here, for example, a part, and then the pages after, you see there's numbers here, the pages after that would be all the technical call outs, tell you what it is, maybe give you some specification on bearings and things like that. So you got a exploded view diagram, and you got these call out specifications. I want to be insistent as an engineer that I get the as-built drawings and I get the as-built bill of materials. I want to know what I got. And it's from this bill of material that we set down in a smart group of people. And here's what the OEM recommends we stock. So let's take that for sure. And then we know how motors perform around here. We know how pumps perform. We know how couplings perform. Let's stock one of these, two of those, three of these. We're going to stock only stuff that's on the bill of material. I only stock things that appear on a bill of material. I don't stock stuff that's not on the bill of material because it doesn't go to anything. I only stock the stuff that's legitimate stuff to stock, and that's how I can be sure that everything I have is legitimate. Here's an example that we can all get our head around. This is a bill of material for a common ink pen. Maybe you guys obviously you recognize it. If this pen was a machine in our plant, and the function of the pen, so now we're talking like a reliability center RCM term here, the function of this pen in our plant was to extend, to write, and to retract. I should have a ballpoint pen here, but I don't have one. So I want the pen I want it to, extend, and I want to write with it, and then I want it to retract. If that's what the function of that pen was in my facility, I would probably put my team together and say, guys, what parts should we stock? Well, we probably need the springs, right? I need this ink cartridge because that's the part that actually writes. I need the mechanism that allows this thing to extend, might include this plunger. And that would be an example. Hey, we need to stock that stuff because that facilitates the function of this machine. Now, what if I had the same machine in a different plant, and the function was not only did it extend, write, retract, but it also clipped to my pocket, like I've got a little pocket clip on my pen here. It'd be the same stuff. It'd be the plunger and this little guy here and the spring and that spring and this ink cartridge, because that's what it allows it to extend, write, and retract. But also now I'm going to stock this clip because that is a function of that asset in my plant. And so what I'm saying, as far as the life cycle of a machine, and if we would agree with the premise that if I put a different part than the machine requires, I put a different part, I'm altering the reliability. And you can take that to mean I'm shortening the life or I'm increasing the cost. I'm doing something to affect reliability. So I'm shortening the life or I'm increasing the cost. But I have to pay attention to what the function of the asset is and make my stocking decisions, stock or don't stock, based on what is the function of the asset. There's a lot of plants and a lot of factories that I would personally go to that would stock every single thing. They would stock every single part for this pen, and they would never use this in a lifetime. They would never use one of these, and that, you know, they would never use it. They might not even use this piece right here. In 20 years from now, I find that I have 17 of these things. I've got some extraordinary cost of my storeroom because I'm stocking stuff. Either it's not on the bill of material or stuff that I would never actually use that has nothing to do with what I'm trying to do. So I want to make real smart stocking storeroom decisions, and it's predicated on this bill of material. If I don't have a bill of material, I'm making poor storeroom decisions because I don't have the document I need to what parts do we actually need? I don't have that document to look at. I wouldn't know. What we end up doing, quite honestly, is we end up stocking everything that's ever failed. I don't have a bill of material, so I'm not making sort of educated and pragmatic decisions on what to stock. But I have experience of all these things that have failed, and I order one and put it in the store. Hey, that pocket clip thing failed 2 years ago. I better order 3 of them. Hey, that spring failed last summer. I better order 2 of those and stock them in the storeroom. And our strategy now becomes to stock everything we've ever ordered. And I end up with a storeroom of stuff that, you know, $600,000 worth of stuff that I may never need again, or has become obsolete as it's set, or worse, it becomes damaged as it's sitting on the shelf because of the dust and the heat and the vibration and the sun and lights and everything. People driving fork trucks, and we've damaged these components. We're not making smart decisions. So I got the spare parts set up, and I know now I need bill of materials. This idea of skilled operators, we're on the subject of strategic planning. I'm going to point out something real quick in strategic planning. When I say strategic, here's where we are now. Here's where we are in 1 year. Here's where we are in 3 and 5 years. When I'm talking strategic, when I use the word strategic, what I mean is we're doing things today to set ourselves up to be successful a year from now, 3 years, 5 years, and beyond. The decisions that we make, everybody on this phone is probably in a position where you make decisions or you contribute to thought. The decisions that we make today, asset-related decisions that we make today, will influence people 10, 15, 20 years from now. If we buy a cheap machine, someone 10 years from now is going to be influenced. If we stock our storeroom full of parts that we don't actually need, someone 2 or 3 years from now is going to be affected by it. What I want to do is set myself up for success in the future. I need to think big picture. I need to think, is that part going to be available 20 years from now? If I got a piece of production equipment that's the main production, and it's got a drive motor on it, that's the thing that drives the whole shebang, is that motor going to be available 3, 5, 10, 15 years from now? That's the strategic thought that somebody around the asset has to have. Am I going to be successful years from now because of the things I'm actually doing today? And one of the things we absolutely need to talk about, certainly today, is skilled operators and skilled maintenance technicians. I've got to build competency. In fact, competence is another ISO 55000 term. We're required, management leadership is required to build competence in our people. So this comes out of one of my books. I said, we've come through the forest of cost cutting to reach a clearing of sober thought and lucid consideration regarding how we put ourselves in a very tight spot. Specifically, we need to get better. We need to get better. This should say get, I apologize. I got that word spelled wrong. We should get better at training operators and maintenance technicians. Now, I don't mean to indict everybody. I don't even know who's on the call, but I'm sure some of you have really robust and really exceptional maintenance training programs and operator onboarding processes. So I don't mean to indict everybody on this assumption that we all need to do better. But Suzuki said in his book on Toyota, he said, skill is the ability to do one's job, to apply knowledge and experience correctly and reflexively in all kinds of events over an extended period. And what he was saying was that the better we get we develop our skills and abilities, not only are we better able to execute those skills, but in crisis situation, this reflexivity he's talking about, in a situation where it's an emergency situation or machines down, it's emergency work, we're better able to ascertain, troubleshoot, make sound, rational decisions using critical thought, critical logic, critical thinking to make good decisions. And so we constantly train on these things and increase our knowledge so we're better able to perform under all kinds of circumstances. The place to start with is to perform a needs analysis and then to perform a gap analysis. So here's the skills matrix. And I want to point out that Mr. Galati, in his book, he mentions that the way to develop a skills matrix in your people, so this is operators and maintenance, it's going to be kind of a grid, if you will. It's to take, list all of your people down the left-hand side. So here's John, and we got Chris, and we got Linda. We got all our people down the left-hand side. It's all the people in our organization, all the maintenance people, or operators, depending on who we're talking about. And then across the top, I put all the things, all the different skills and abilities they need to know how to do. This is a very important distinction. Not what they know how to do, but what we need them to know how to do. So I've got a list of all my people down the left-hand side. This is Mr. Galati's out of his book. And this is all the things that they need to know how to do. And I set up this grid. And then, and believe it or not, this is actually the process to develop this a gap analysis. To set this up, I simply ask everybody, based on this, I ask John, what do you know how to do? And John's going to say, well, I know how to do this. I know how to do this. I can do this, and a little bit of that. And Chris is going to say, I spelled Chris wrong. Chris is going to say, I can do this, a little bit of this. I can do, some of that. I can do this. And Yolinda's going to say, I can do this. And that's pretty much, and maybe I can do this over here. So I can see where I have gaps in my talents and my abilities. I can see over here on this one, I'm real weak because nobody knows how to do that really well. And so once I put this grid together, and this is literally how you do it. All the things that people need to know how to do. And I ask the maintenance technicians, what do you need to know how to do? And we weed through that, what we actually want them to know how to do. And then through some amnesty program, the first thing you do is ask, okay, based on this, what do you guys know how to do, and to what level do you know how to do it? And so one time only, a little amnesty program, everybody gets on a piece of paper what they feel their competence and their competence level is. And then I'm looking at something that looks like this. In fact, this is this actual device, this grid, this Excel spreadsheet is the one that I actually use. And I got a little legend off to the side. If you got 4 squares filled in, you're fully capable of performing and you can train others. If you got 3, you're capable of performing it on your own. If you got 2 squares in that block, in that cell filled out, you can perform with coaching. And if you've got only 1 square filled out, you're in training on that particular topic. So I put all the people's names down the left-hand side. I put all the things they need to know how to do across the top. I asked Bill and I asked Randy to fill in based on this legend over here. And then once I've got all that, I say, that's it. That's where we stand. And I take a look at right here and I go, I got nobody that knows how to do this. I got a guy in training, that's Randy, but I've got nobody that knows how to coach anybody. I got nobody that can perform it without coaching. I've got a real concern there. And so that now becomes, for my gap analysis, I would say, I need to create or have a training curriculum or means, a mode of training people to set up the Rockwell tester. Because at the current time, this is a gap in my competency and a gap in my abilities. And I do that for maintenance and I do it for operations. And it even can translate to staff positions, my storeroom people, my planner, maintenance supervisors. They have skills and talents they need, like even presentation skills and opening and closing work orders and those kinds of things. So I've got to perform this very high level maintenance, training, and operations. I got to have this sort of gap analysis. I got to have spare parts I got to set up the training, the knowledge and skills, and the spare parts. I got to have processes that ensure my success with that asset 10, 15, 20 years into the future. I got to have somebody that knows how to do something in the now and in the future too. On the subject of capital and general modifications, I know these are different depending on what agency we're dealing with, but organizations engaged in capital equipment purchases or expense modifications need to take into consideration the whole process. I want to engage the hourly operators and technicians in the design, build, and install. And you saw that as equipment design excellence. And consider spare parts. These are huge parts of fielding a very successful asset. I get the people who are going to have to use and work on this machine. I get them around the table to discuss the design and the build and the install. And also I ensure that we're using parts that we're already familiar with. I want to remove parts no longer required with the new equipment. If I'm getting a new press in, is there any equipment with the old press going out, or conveyor system or oven or whatever? Is there any equipment I can move out of the storeroom? Is there any parts that I can obsolete and get rid of? Can I clean out the storeroom? I've got to create those preventive and predictive strategies around the new equipment. And by the way, and this isn't it's not the case necessarily in the US, but I want to have spare parts in the storeroom before I start the machine. And I want to have a PM and predictive strategy before I start the machine. Very often, these are left till after the machine is actually running. So what we've just done is put in a new $100 million production line, and I don't have any spare parts in support of that line in the storeroom. I don't have any parts. And I don't have any strategy, preventive or predictive, to keep it running. That's not even a good business decision, but that's how we end up. That's where we end up. We don't, we're not thinking about that because we're in a, we're trying to get the machine in the ground. So someone was, again, great questions, guys. Does the skill matrix have greater influence on selection criteria and staff turnover to effective utilization of staff rather than more time spent on training? Yeah, that's good. First of all, the first part of that, if I have a really good training matrix, and somebody really appreciate the matrix, if I have a good training matrix, I'm better able to put up a notice that I need somebody that has some of these qualifications, or at least has an aptitude to learn these qualifications. So I need somebody to put in for the job that feels like they have some competency, that they can learn these skills. Here's the job, here's the kinds of things you're going to be involved in. Are you able to do some of those, or do you feel like you can do all of it? Can you be trained to them? And also on the turnover, I think if people have a real idea that we're investing in their training and that we have a place for them in the future. Again, this is strategic. Hey, I need you in the future now, but also in the future. And here's what I'm willing to commit as a company. We're willing to commit to this level of training, and there's usually compensation along with people. You learn more skills and ability. You get paid a little bit more. That's very typical. And so I'm not just training for training purposes. I'm not just training to fill a square. I'm actually training for the purpose of closing those gaps. I'm doing this target training. These 3 people on this subject, those 2 guys over here on this subject, I'm sending her away for training somewhere to come back with this knowledge. So it gives me a real strategy how I'm going to apply my very limited training budget to close some gaps. Otherwise, I'm just training everybody and nobody knows how to do anything. Everybody gets trained, but nobody knows how to do anything. I would suggest, and probably some of you guys have a really robust management of change process, because I suspect that many of you guys are probably engaged in some sort of environmental or safety concern around highly hazardous chemicals. In the US, it's our OSHA organization that runs a process safety management. And for example, food companies have a lot of anhydrous ammonia for cooling purposes, chilling purposes. And so you have to have an MOC. It's part of the management of change, or you have to have an MOC. It's part of process safety management. So if you don't have a change process, I recommend that you have one, because as I'm changing things, I want to be able to document what I'm doing and make sure it's clearly technically feasible. So here's an extending an asset's life, because I was on this trajectory right here. I was going to get rid of that machine right there. But through asset based decision-making discussions with key players, at this time right here, the organization said, let's make a modification. Let's do a modification to the machine. So I got a little bit of a DBI going on here too, right? And so what I've done now is instead of 10 years on this machine, I'm doing a modification that I believe is going to extend the life to 20 years. Now, it's important to know that I've done that. There's a really good chance that this modification right here was not done to increase reliability. It was done to increase the longevity or to change it in whatever it's producing to make it produce a different product. There's a lot of components on this machine that didn't get enhanced or improved. I got a lot of things that are 10 years old or 15 years old, and now I'm going to carry those out for another 10 years. I'm not going to have a happy, this is probably isn't going to be happy and joyful for the next 10 years. I'm probably going to start seeing defects and failures and things I never anticipated because I only built my program for 10 years. So when I'm extending the life of the asset, I've got to go back now to spare parts and take a look at my strategy. I got to go back to my training, take a look at my strategy. I got to look at my operator training, take a look at my strategy. And I've got to start to consider the cost of operating this thing because, you know, electricity costs, energy cost, air cost, things could have gone up on this thing and someone's got to be tracking that. So it's very routine to extend the life of an asset by doing some sort of modification to it so I can get it to last a little bit longer because I don't have the capital money to buy a new one or there's no real need to buy a new one if I can just kind of modify this one. But I need to know that that's affecting a lot of things because I'm not changing every single component on that machine. I'm just changing a few of the relevant things, but the machine is still going to be really, really old. And again, the age doesn't affect it so much if I've really been taking care of it. But if I just let that machine go, now I'm going to have a really bad machine, or I'm going to have real concern about this machine. So that's something to keep in mind when we're extending the life. It's vitally important that those responsible to track asset performance and its value return take steps to update asset management plans. So if you're in ISO 55000, I'm now changing the context or the environment of operation of that asset. I need to make an actual document, a notation that here's what we did, here's why we did it, here's what we're anticipating, here's what we think is going to happen, and here's what we've done to mitigate those things. You know, our strategy on the upkeep of that asset has changed because we've changed the machine. We've done something different. We need to change our strategy. Maybe not drastically. It might be some final, some fine tuning, so to speak. Okay, so I want to show you a couple of case studies, and this is the actual scenario that introduced me to. We didn't call it life cycle cost or engineering, or I'd never heard of Ramesh Gulati. He never wrote the book. This was back in 1986, so none of what we've been talking about was known to me. I was in the military, and I had a good friend who ran the motor pool on base. He was a second lieutenant like me, and I was in charge of aircraft maintenance. I was an aircraft maintenance officer, and Terry was in the motor pool, and he was in charge of the fleet of cars that the Air Force had on our base. So we had, it was Air Force, so we didn't have tanks and things. We just really had staff cars for people of senior officers to drive around in. So here's the scenario. Here's the case study. I'm going to give you guys a chance to read through this, and then we'll come back to this. So just read through it. So here's the scenario. This was in 1986. The Air Force, at the time, the Pentagon didn't have as much money as they got now. The Air Force, the only kind of vehicles we had for the most part in the motor pool were just sedans, just staff cars really. And they were a very cheap car, $8,600, brand new, delivered to the base with Air Force blue paint and the stickers. And they didn't even have any nice features. It was an AM radio and roll-up windows, if anybody remembers those, and manual locks. So every car arrived at our base, brand spanking new, $8,600, landed at, that was the cost. The DB&I commissioning and everything was $8,600. Every car came with it, and we didn't have computers back then, quite honestly. Every car had essentially a bank account that had $10,000 in it. Every time any maintenance was done on the car, aside from oil and fuel, maybe oil counted in, but aside from fuel, anytime maintenance was done on the car, I don't think oil counted, they would subtract that money from the check register of that individual car, which was tracked by the vehicle identification number. So there were 100 staff cars, 100 checkbooks, and at any given time, there was money being subtracted. Once that checkbook for that car hit zero, once there was no more money left, the car was sold. It didn't matter if the car was brand new and it just had a bad engine we had to replace, and that was $10,000 or whatever. Somehow we ran over something and damaged the undercarriage and it cost $10,000 to fix. It didn't matter how old the car was. They got rid of the car as soon as it hit $10,000. And I asked Terry, my friend, I said, why is that? And he said, because we have 100 cars here, John, and there's 100 bases around the world. There's probably not maybe 100,000, but there's several thousand of these cars in the U.S. Air Force. We could be, there's a term in the States, nickeled and dimed to death. I don't know if it translates into, again, whoever called in and what's customary there. But if we keep fixing cars all the time without paying attention to how much they're worth, we end up spending a lot of money on a car that is worthless. So the Air Force, instead of, the Air Force just decided, let's just track the cost, let's just cut our losses and run. Let's try to keep the cars for as long as we can, do good maintenance on them and train people how to drive them properly, and we'll get more life out of them. But at the end of $10,000, we're done with that machine and we're moving on to a new car. And that's just the way they did it. Now, this is in 1986. I had never heard that. I just came out, I've only been out of college for a year. I had never heard that philosophy or approach. It seemed to me like just a regular person, like a real waste of money, because I tend to hold on to cars for a long time. I pay them off and then I hold on to them for another 5 or 6 years because I don't like car payments. But Terry said that's the way the Air Force does it. So read the rest of this, read the rest of this case study. What Terry was telling me was that the Air Force knew how much money they had invested in the car. And they knew with all likelihood that if the car was a bad performer, it was only going to cost more money over time. The Air Force made a very strategic asset management decision to say, we're going to spend this much money and no more. That's not an approach that we should shy away from. It's an approach probably in our businesses. We should at least understand and make business decisions, asset business decisions, based on the criteria that we set up. So we're not spending $2.3 million on a machine that only costs $300 brand new. So what I've done was I've taken Ramesh Gulati's table up here to the right, and I've reconstructed what I believe Lieutenant was telling me. He was telling me that a brand new car at this point cost $8,600. If I use that as 45% of my cost, $8,600 is 45%. I could assume then that this is about $1,000 over here. That gives me over the life of the car, the operational life, which starts right here. That means I have $9,555 to spend, or essentially $10,000. That was the model. That was the curve that the Air Force was using. They hoped that the car would last a very long time. But if I only got to this point right here and I'd spent $10,000, I'm done with the car. I'm getting rid of it. If I made it, if this was 1 year, that's fine. If this turned out to be 7 years, that's fine too. But I was cutting my losses at $10,000 because there's not enough value left in that machine to make up for the fact that I've already spent everything in the bank on it. That machine has no more value because now I start having negative value. I start going under or submerged basically on the value. So that was what Terry was telling me all those years ago. Here's a scenario I want you to think about that's more kind of today's real life scenario. Let's say we're going to buy a new conveyor. Here's the case study. I want you guys to read this. I pulled this out of my book, so that's why you see references to my book. Okay, so we're going to buy a brand new conveyor system. It costs $250,000 or $250,000. We're going to depreciate this thing over 10 years. So our usefulness of it is for a 10-year period. And at the end of that, if we care for it and operate it properly and and we've done all the stuff we're supposed to do, that conveyor will still have a value of $50,000 at the end. And we're probably going to sell it for $50,000 and someone will buy it because it's a good conveyor and still got some life on it. So this is what I've done here is I've taken Ramesh Gulati's table. And if you remember, as a matter of fact, let me go back to it. Or did I put it on the curve? No, I didn't. So let me go back to the slide where I've got Ramesh Gulati's curve. Oh, you know what? That's so far back I can get to it. But if you remember, he said that for non-DoD, so this is general industry, he said the design, development, and installation phase of the curve ought to reflect anywhere from 15 to 30%. So the front part of the curve is going to be 15 to 30. The disposal's a constant at 5%. That means in the middle or the operating, the M&R cost is going to be anywhere from 80 to 65%. Okay. So, and here's what I'm driving at. In my organization, engineering, maintenance, purchasing, production, leadership, we need to sit down and make a decision that the Air Force made in the 1980s. Our company, the John Ross Company, when we buy a new asset, we want, as much as we're able to influence it, we want that asset to reflect for the life cycle cost. We want it delivered, installed, and operational, and we want that to be representing 20% of the life cycle cost. I'm making that decision that from now on, every piece of capital equipment we buy, whatever the cost of it is going to be 20% of the cost of the life cycle of what we intend to have it for. And we're going to make decisions based on that number. And let me show you the decisions that we're going to make. Because as soon as we lock into that, what we're saying is 75% of our life cycle cost is going to be $937,000. The total cost of ownership of that conveyor in 10 years, the total amount of money we're ever going to spend on that thing is $1.25 million. Remember, it costs $25.25 million to begin with. Do you remember that Lieutenant Terry said a car cost $8,600? They would put in a bank registry $10,000, and to get rid of the car cost $1,000 because we got to tune it up and stuff and take the paint labels and things off of it and sell it somewhere. The Air Force said that we're only ever going to spend $19,600 on a car. My company is saying for a machine that costs $250,000, the most life cycle cost we intend to spend on it is $1,250. That includes the purchase price, includes the disposal cost, and includes the M&R cost. And here's what that looks like in real life. So using this table right here, if we utilize our decision-making criteria that we're only getting the 20% of the cost is going to be reflected in the purchase and delivery cost. What that means is when I start the operation of the machine here, put it in operation, I have essentially roughly $940,000 to spend over 10 years. And again, all things being equal, and I know this isn't how it really works out, but what I can say as a maintenance manager or a plant engineer, I can budget $93,700 a year for the upkeep of that machine. And what do I mean by upkeep? I mean the preventive maintenance, predictive maintenance, corrective maintenance, spare parts, upgrades, modifications, everything that we do in maintenance has to fit into this budget. And if I maintain the equipment, it will last for 10 years. Remember, that was my plan. It will be worth $50,000 when I'm done because that's what I projected I would have. And I'm only doing maintenance, but I'm not doing the maintenance we're doing now. I'm doing really, really good maintenance. I'm paying attention to good, recognized, generally accepted good engineering practices. That's a term right out of engineering. So I'm doing really good maintenance. And every single year, I am checking to make sure I still have 9 years worth of value. I've only spent 1 year worth of money. I've got 7 years worth of value left in the machine. I've only spent 3 years worth of the banking account. I've got 8 years of banking account spent. I've got 2 years left, and I still got 2 years left worth of value. I'm suggesting in my buildup on this life cycle cost is that we have the ability to influence the design, the build, and the installation by simply saying, here's what we expect. Here's our position. Here's what we will accept as far as standardization of parts. Here's the documentation that I want. I'm going to compel people to understand that the sticker price of the car is not the life cycle cost, that it's different, but I can control that life cycle cost if I do really great maintenance, but only if I buy a machine that is designed to do what we're going to do. If I buy a machine that's just a lousy machine, I'm not even going to get 2 years into this thing and I've spent all the money on it. And some of you guys on the call are probably in that position. You fielded a machine that wasn't a very good machine, and nobody was pleased with it, and you got 3 years in the utilization of it, and you've run out of money, or you're spending money, you're in the negative category now. But I wanted to impress with this webinar upon my fellow professionals that we actually control this, and it goes all the way back to the concept of inherent reliability and the fact that we are responsible in the sense that we have the ability to sway people and convince them of the proper design, proper build, proper installation, that we do really great control activities, which is the maintenance. I mean, really perform at the highest level, that we understand that the asset has to deliver value over the period of time that we've determined we need it to. And that if we use this table, this is something that you get really good at when you start practicing. If we first go in and take Ramesh Gulati's range of cost, and we decide as a leadership group for our organizations that what we want to do is field a machine that represent the cost of fielding it and commissioning it represents 20% of the overall life cycle cost, we will have plenty of money to maintain it over those 10 years. Now, I just picked 20%. You guys could go with 15% or 30, or you could go with 27% or 18, it doesn't matter. I just used 20% as an example, but I have to have that number and I have to have that discussion in the front, and then that becomes the model by which I control all my asset life cycle costs and spending. And when I run out of money, I evaluate, do I still have a machine that's worth anything, or do I need to just get rid of it and cut my losses and run? Or if I run out of money, does this thing still have 5 years of life left on it? And if you've run out of money in 5 years and you still got 5 years, you're probably going to have an asset that you're going to end up spending a lot of money on. And you're in the negative, by the way. You're in the negative on the money. Wow, we've been at this for 2.5 hours. That was a very enjoyable presentation on my part for delivering it. That ends my presentation. I hope that you found this helpful. There's some great questions. I do want to mention while we're still on the phone, one gentleman asked, and I think I mentioned this, if LEORON could maybe put on this seminar, this webinar again, and he gave me his email. Some of the gentleman gave me his email, and I'll be reaching out to LEORON, and I'll give them your email to do that. So I see we got some questions coming in before we wrap this up. Thanks, interesting, great. Okay, good. Guys, I appreciate the comments. I just wanted to share with you, what I actually do, in the sense, these are the tools I actually use. So I didn't want this to be some webinar where I read somebody else's book and I'm telling you everything they did. I want to share with you what I do. I think, again, I don't know you folks, but I wish you well. And I hope that you found some of this useful and put it into practice. If you need to get hold of me personally, please go through LEORON. They'd be happy to pass on any message. And before I do sign off, and Chris, I know that you're monitoring. I don't know you folks, but I think as a world, we're all in this together as far as this virus that is absolutely impacting everybody. And I want, from my little humble heart, I want to wish everybody and your families great health and prosperity. And I certainly hope that you're enjoying only goodness, and I mean that. And so thank you very much for your attention and time. I've really thoroughly enjoyed this. Chris, thank you for the opportunity to share a little bit that I know and can do.
Okay, I'm back on. Just to thank all of you once again for participating in this amazing webinar. Thanks to you, John. First of all, it was really amazing. And as I see, all of the guys liked it. So if you have any questions, any concerns about what was mentioned today, something you're not aware of, something you want to know, you can always reach out to me, and I'll address some questions to John so he can answer. In the meantime, also we're running few trainings, live virtual trainings. They're really interactive with John Ross. Next week we're starting the best practices in maintenance reliability, which will help you to prepare as well for the CMRP examination if anyone is planning. And the week after, we have as well the best practices in the maintenance planning and scheduling. The same courses along with the asset management work processes, again, will happen in June and July. So whoever is interested, you can reach out to me and I'll share more information about those topics as well. Nothing much to add. Thanks once again for all of you participating. John, thanks to you.
Thank you.
We'll have the presentation most probably done in a day or two, and I believe it will be available as well for all of you to have it. Yeah, that's it from my side. Anything else to add on this, John, or we're good?
No, again, just stay home, wash your hands. You guys be safe, and thank you.
Thanks to you as well. Have a nice one and enjoy the evening. Bye.
Okay, bye-bye.